My name is Eugen Družin, and today I'm going to talk to you about EIP-4844 and how it enables us to get a transaction cost below 1 cent. But first, let's get to basics. What is Ethereum and what is gas cost? So Ethereum is a decentralized system that enables us to develop and deploy smart contracts, and around that build the applications. Because the system is distributed, it has a limited amount of resources. And everybody wants to use resources, it becomes more expensive, and for each interaction, the user has to pay some gas. So when we get more users, each transaction will become more and more expensive. So to tackle that, we need to provide some solution. And here we have scaling. For scaling, there are different solutions. One is sidechains. We have like Near and Solana that can be on EVM or non-EVM, and layer 2 solutions. We have optimistic rollups and ZK rollups. Here is Optimism, Arbitrum, and Starknet. You probably know, I hope that somebody got airdrop from here. And you can see here, like, this is the Ethereum roadmap for improving, scaling, and multiple solutions. It's divided into 6 stages. You can see a lot of details here, but the important thing is each of these 6 stages is done in the parallel. So every solution is independent. Some are mixed, but main thing is all is done in the parallel. So the first thing is like the merge. We switched from proof of work to proof of stake. I hope you know about that. The second is the surge. We are going to focus on that in this talk. It is about improving the scalability and data sampling to improve rollups. And the other ones are not in the part of this talk. So. Now let's focus on the first two. On the first two, before the merge, we had a Beacon chain launch. After the merge, there were withdrawals enabled, and now there are improvements around single slot finality. Here for the surge, as we said, we want to improve the scalability and number of the transactions we can do on the rollups. The main thing is to get EIP-4844 implement. We got it. And the later stages are going to focus on data availability sampling to enable even better scalability. So the merge. We had the execution client that is responsible for executing transaction and storing the state. And we added another layer, it's consensus layer, that is responsible for proposing blocks and validation of that blocks. Here we have a popular Panda meme. It comes from the merge when we had one layer, added another layer, they merged, and we got the popular Panda and Ethereum 2.0. So this is how the Ethereum node looks like today. We have one node that is running 2 different clients. One is consensus client, and another one is execution client. They talk to each other using standard API. So let's get back to rollups. Rollups are interesting because they derive their security from the mainnet because they publish the state changes on the mainnet. That data is needed on the mainnet because to prove any invalid transactions. But as we know on rollups, there is like 7-day withdrawal period. And after that, those 7 days, the data could be basically thrown away or deleted. And we can see this will be the bottleneck because we are storing the data that is needed only for a short time for forever. And let's check the Etherscan. We had a standard transaction. It comes from Optimism Batcher. This is transaction type 2, and we can see a lot of data here in the input. So the main thing is we need to get rid of this data to make transactions cheaper. And how do we do that? Here comes the EIP-4844. It brings another type of data, blob data, that will be separated from the call data. It will have a shorter time period. It will be discarded after 18 days. And popularly known, it is called also proto-Deng sharding, about the two people who were working on proposing this solution, like Denkrad and Proto-Lambda. So this is how it will look like. We have multiple L2 solutions, EVMs. Each of them are proposing their own blobs. Blobs will get to the EVM and to proof of stake. So this is how it will look like. So what are the blobs? Blobs are new transaction type that provide us cheaper data that will be discarded after 18 days. The important thing is that data is not accessible to the EVM, but it's stored only on the consensus layer. That's why it was needed. If you remember, we had two clients running on the Ethereum node. One is execution, that is executing transaction, and the other one was consensus layer that is proposing new blocks. If we store the data on consensus, we can discard it after some time. Now to kill you with some details, blob, what is a blob? Blob is basically a vector of 4,096 finite elements. But let's get to the definition, how it works. We have a blob that is basically a vector, as we said, of 4,000 elements. From that, we calculate KZG commitment. Then we are using this KZG commitment to calculate the hash. As you see, KZG to versioned hash is the final product. And this versioned hash will be sent to EVM. And a little more about details. To enable blobs, we need to add new transaction type. It will be type 3. Blob commitment, each commitment will have version. Currently, we only have version 1, but it enables us to add new improvements by changing this version number. Maximum number of blobs that can be stored on the block currently is 6, and it will be changed to 16 after some improvements. And target blobs per block are 3, and it will be changed to 8. If this sounds familiar, like having the maximum and target values, it's similar to EIP-4844 that enables us to use the target gas and the maximum gas. When the current gas is above the target, the transactions become more expensive. When it's below this target value, the transactions will become more cheaper. The same goes for the blobs. When we have blobs above 3, it will become more expensive. When the value is below 3, it will become more cheaper. And here is the cycle, how it works. We have L2 users that publish their transactions to the rollup sequencer. The sequencer will then batch multiple transactions to make them cheaper, run the transaction, and publish the data on the L1 transaction pool. From the transaction pool, we have nodes that will take the transactions and create a block. Here we know that the block will contain a new type of the transaction type 3. But the important thing is you can see the blob is not inside the block that is added to the execution layer, but it only has a reference, versioned hash, to the blob. It's important to notice that this blob is not part of the block, and it can be discarded after 18 days. So you can think of blob as a sidecar to the block, because the block can live without the blob. Blobs are only reference for the transaction type 3, but the blob cannot be added to the block without references. And also important thing is it is always the fixed size of 128 kilobytes. It doesn't matter how many transactions are inside the blob, it will have always fixed size. Now let's see how it looks on the Etherscan. We can see that base batch sender, we can think of it like rollup sequencer. This will be the batch sender. And let's go to the details. We can see that we have 6 blobs in this. transaction, and the transaction type is type 3. And here you can see input data. Before it was very large chunk of data, now it's 0. So to move to this from the block perspective, block has 6 blobs. We can see that the size is 6 times bigger. And let's move to this specific blob. You can see like it has a versioned hash. It starts with 1, value 1 that is specified. And here is the blob data. Before this, all data was in the input data, and it was all published to EVM and execution layer. Now this data extracted and lives only on the blob. We could see like in details, as we said, we have execution client. Execution client has block inside that is stored on the EVM. It has type 2 or type 3 transactions, but type 3 transactions have only blob hash. This blob hash references the outside slot that is inside consensus layer, and we can see that this sidecar contains the blob data and KZG commitment, but only versioned hash is stored in the execution layer. You heard about saying KZG a lot. So what is KZG? It is a new cryptographic mechanism that is used for EIP-4844. I don't know if you remember like KZG ceremony. It was needed for the initial secret key for the setup. I don't know if anybody signed it. Basically, you had to generate secrets, signed it, and publish it to others users to sign it. More than 100,000 people contributed it. It's specific because if only one user keeps the secret, the final secret will be safe. So I signed it. If you trust me, this setup is safe. So we talked about proto-Deng sharding, but what is needed for the full Deng sharding? Let's talk about sharding at first. Let's use a reference of the standard database. We have like multiple items and the prices. And we will shard it on the one item. We will use price. So basically we use items below $50 are in one table, between 50 and 100 will be put in another, and above 100 will be put in the third. So basically this is a standard database sharding. But here in the proto-Deng sharding, it works a little bit different. Here comes the data availability sampling. Basically, this is it. It enables us like to prove that all data in the blob is available by only sampling specific items. This enables us for the clients to download only part of the data, but to be sure that all data is available. Without data availability sampling, we would need to download whole blob to verify that all data is available. Another solution needed for the full Deng sharding is proposer builder separation. Proposer builder separation will enable to have like 2 different clients. Proposer will be lightweight clients that will validate blocks more easily, so they can be really cheap minimal machines. And the other type are builders. Builders can be heavy machine that will generate the blocks, and this enables us to get even better compression of the data, like better machine can provide better compression of the data and enables us even cheaper transactions. And we come to data availability. Why is it important? We have the layer 2 sequencer that is batching, and we have this path, like data on chain, execution to data chain to execution layer as call data. That was before EIP-4844. Now we have this path, sequencer, data on chain, and the data is stored on the consensus layer as blobs. But with future improvements and data availability, we will probably have some other types of storing this blob data as outside chains, but we will see how it evolves. This is only the start. And just to recap it, we have like 2 different spaces that we stored the data. First, it was block space. It's stored on the execution client. EVM has access to it. Now we added the blob space. We have the data is stored on the consensus layer. After 18 days, this data can be discarded. This enables us to basically have the cheap transactions. How cheap? Let's look. We get like 10,000x cheaper transactions. We can see here like different L2s. Every transaction is below 1 cent. Blobs basically enable that. So here Coinbase was tweeting after the hard fork and the implementation of EIP-4844, the transfer on the base chain, USDC token transfer went from 30 cents to below 1 cent. Also, like other solutions are tweeting, transactions are really cheap. And we can see here, like, this is what was the L2s paying on the mainnet. In the blue color, you can see the call data. The call data is the most expensive part that was paid by L2 chains to L1. And now, when we removed that expensive call data, this enables us to get the cheaper transactions. Little bit of statistics. It's from 18th of May. We can see more than $95 million is saved compared to using call data and now using the blobs. It's a huge improvement. We have like 19 gigabytes of blobs data until date. Who is using the blobs? We can see like Base mostly, Arbitrum, Scroll, probably you know all those L2 chains. And that is it. If you have any questions.
Hey, good presentation. Can ETH scale to 100K TPS with 8 blobs a block?
Sorry?
Can ETH scale to 100,000 transactions per second if we're maxed out at 8 blobs per block?
No, basically the main idea is to have Ethereum mainnet as the consensus layer and use its security. We are publishing transactions to rely on its security in the end. And this, we are using rollups for the execution and basically storing that final state. And usually, before blobs, it was pushed to mainnet, so we had to pay the gas on mainnet for storing the data. Now we only push that version hash.
Yeah, but there's still, it still has to end up written to L1. So I understand it's going to consensus layer now, but
yep.
If we can only write 8 blobs worth of these rollup transactions to the consensus layer per block, and if the surge's goal is 100,000 transactions per second, is that enough to get us there, or do we need like, yeah?
As we see, we need more improvements, like to get us more blobs per block, because now it's limited only to 6. It will be changed to 16. And also another type of compressions, like this is the first version of the compressions. In the future, there will be even better and better compressions, so we will be able to store even more and more data with only minimal version hash on the mainnet.
Cool, thank you.
Hi, thank you. Do you know any usage of blobs other than L2?
No.
Thank you for the nice presentation. Does the lower gas costs reduce the security of L1? Is there less incentive for stakers?
Less incentives for stakers? Probably because it enables users to get cheaper transaction, and the cheaper transactions are the nodes on the L1 will get less of the base fee, how it goes. So For the stakers, basically, they want more expensive transactions in the end. It's because they will earn more money, but in the end, users want cheaper transactions to do more transactions. So you need to find the balance. Okay. Thank you very much, and see you.